been hearing from the previous session, there's just a tremendous amount of new technology that's being uh, enabled for all kinds of new science as well as clinical applications. Uh, and the focus of today's session is really going to be some rising stars, some really pioneers in the area of naturalistic recording in humans, as well as some sessions later today to talk about how this is being done in non-human species as well. So our first presentation, what we'll do is have remarks from each of our speakers. As usual, please do leave comments in the chat window and questions for our speakers in the Q&A tab if that's working for folks. And we'll come back at the end and try to have a robust discussion of everybody. So our first speaker is Olusola Ajilore. So Olu is an associate professor in the Department of Psychiatry at the University of Illinois, Chicago. He graduated magna cum laude from Harvard with a degree in biology. He then went on to get an MD PhD at Stanford, where he studied the deleterious effects of stress hormones on the brain. And then he joined the research track residency at UCLA, where he trained as a psychiatrist and then transitioned into studying the neuroimaging correlates of major depression. His lab currently uses computational neuroimaging techniques and digital biomarkers to better track and treat neuropsychiatric disorders. So with that, I'll hand it over to Olu for the first presentation. Thanks.
All right, thank you, Justin, for that kind introduction, and thank you to the organizers of this summit. It's a real privilege and honor to have the chance to showcase some of our lab's work and to be on a panel with some excellent panelists. So today, the title of my talk is Real World Mood and Cognitive Assessment for Real Life Impact. Let's see if this works. Okay, great. And here are my disclosures. The work I'm going to talk about was funded by the Robert Wood Johnson Foundation, as well as NIMH. So by way of overview, I'm going to do a brief introduction and talk about one of the apps that our lab has developed called BioEffect and how we're using it in a study called Unmasked. And then I'll end on a new study that we're just getting started working on digital interventions. So I always like to look to the past for insights that might inform what we do today. And I came across two passages that I thought were very relevant for the discussion that we're having this afternoon. The first was published in the American Journal of Insanity in 1891. And there's a passage in an article called The Mechanism of Insanity by Edward Cowles that I thought was very relevant, where they talk about how our clinical assessments have greater value when by careful study and comparison of our symptoms with the action of the normal mechanisms by a like, quote, tireless observation, then our assessments can be done with more completeness and precision. And then there was also an article that was published a little bit earlier in 1859 in The Lancet, where they talk about how when a patient is admitted into the asylum, they're displaced in time and in place from all the things that might be contributing to their illness. And that when we sort of dislocate the patient from that context, quote, the surrounding conditions, that our diagnoses can be void of precision and authority. So we see that notions of precision psychiatry existed even back in the 19th century. But what we have now in the 21st century are tools for these, quote, tireless observations in our surrounding conditions, like smart phones, smart watches, smart speakers. And so all of these tools can be used for this tireless observation, which we now deem ecological momentary assessment, or EMA, ubiquitous sensing. And these tools can be used for repeated assessments or collection of real-time data of our behavior, our experience in natural environments, to quote Stone and Schiffman, who came up with the term EMA. And our lab has looked at EMA and passive sensing, as others have, to address some of the problems that we have with our current modes of clinical assessment of mood and cognition, as was hinted at by some of the keynote talks this afternoon. So for example, there are a lot of reporting biases that occur when we assess our patients, whether recall bias or recency bias. Oftentimes our assessments are asynchronous, and so we're not actually assessing how our patients are doing in between our visits. And then they're also subjective. A lot of the conditions that we treat can actually influence how patients observe how they're doing. Oftentimes, when I'm treating patients with depression, I'll ask whether their spouse or their colleagues or their friends have noticed any improvement before the patient does, because oftentimes there'll be other signs of improvement that the patient isn't aware of or doesn't have insight into. And then the other thing is that we do these assessments in artificial environments, either in clinic or lab settings. And the data might be much richer if we could capture them in naturalistic real world settings. And so our lab has tried to use, or is planning to use passive assessment in a study called unobtrusive monitoring of affective symptoms and cognition using keyboard dynamics. And our goal is to combine the work that we've been doing in neuroimaging with our emerging work in digital biomarkers to see if what we measure with these devices, whether they track with what we can measure in the brain. And this work was kickstarted by my colleague, Dr. Alex Liao, who developed an app called BiEffect, which won the Mood Challenge for Apple's Research Kit. And this is an app that replaces the default keyboard of your smartphone with a customized keyboard that allows us to track how the user is typing. And so importantly, we don't track what the user is typing for reasons of privacy and confidentiality, but by tracking how the user is typing, we can collect all kinds of keyboard metrics that might allow us to infer information about the user's mood and cognition. And those metrics include things like the speed of typing, whether people are making mistakes when they type, the use of backspace or autocorrect, the length of their typing. And one of the first projects that we did with BiEffect was done in conjunction with our colleagues at the University of Michigan, Dr. Melvin McInnes and Dr. Kelly Ryan, who've been working with the Prechter longitudinal study of bipolar disorder for several years. And so we were able to equip the participants of this study with an Android version of BiEffect. They also completed daily ratings of mood, impulsivity, energy, and rapid thinking. And we also had weekly clinician rated scales of depression and mania. And one of the first studies that we published out of this pilot was done by John Zulueta, who's a junior faculty member in our department. And he fed all of these keyboard metrics into a linear regression model and showed that they were significantly associated with clinician rated scales of mania and of depression. And then he did a deep dive to see which of the features were unique to depression versus mania. And he found that backspace usage was uniquely associated with manic symptoms, such that less backspace usage was associated with more manic symptoms. And then autocorrect rate or typos were uniquely associated with depressive symptoms, such that more typos were associated with more depressive symptoms. Now, this was done cross-sectionally, and we had another colleague in our department, Jonathan Stange, who's now at USC, who wanted to look at data from a particular time period and see if instability in the data within a particular time period could predict increases in clinical symptoms 6 to 8 weeks down the line. And so the question he was asking was whether we can prospectively predict changes in mood symptoms using our baseline, either BiEffect-based measures or EMA ratings. And so what he was looking at was the variability of daily mood ratings and the variability of daily typing speeds to see if controlling for baseline symptoms, they could predict prospective increases in symptoms. And he found that, yes, both instability of daily mood ratings as well as instability of daily typing speed were significantly associated with future elevations in depressive symptoms. Now, we were fortunate in that these participants also did a neuropsychological battery, and we looked at two of the tasks out of that battery, the trail making test part A and part B, which assesses processing speed and executive function, and the Tower of London task, which is also an executive function task. And we wanted to see if the typing metrics that were successful in predicting changes in mood and current mood states were also associated with cognitive function. And so this was work done by Mindy Ross, who looked at the trail making test part B, which was done twice a day in these participants. So they did it in the morning and in the evening. And then she divided key presses up between the first part of the day and the latter part of the day, associated the key board activity in the first part of the day with the morning trail making test and the ones in the latter part of the day to the evening trail making test. And then she found that there was a significant association between typing speed and trail making test duration, or the time to completion. So the slower they were with their typing, the slower it took for them to complete the task, right? Slower their processing speed. What was more interesting is that she also saw this within subjects. So that within subject variability in typing speed was associated significantly with the within subject variability in their performance on the trail making test. And this is really important for our sort of hope for this type of technology to be able to detect individual patterns of what's quote unquote normal, and then be able to detect deviations from that. So the other thing that we've done is we've looked at this keyboard data like a time series, and taken a dynamical systems approach to look at sample entropy in the time series data. And this is a technique that's been successfully used in a number of other fields, like looking at EEG data or looking at heart rate variability. It's also been used to look at postural sway in the context of Parkinson's disease. So we characterized our keyboard data according to make it look like a time series by plotting typing speed on the y-axis as measured by the interkey interval as a function of key press order. And it's color coded according to the type of keyboard event, whether somebody is pressing an alphanumeric key, whether there was an autocorrect event or backspace press. And we were interested in looking at the Tower of London performance as a time series as well, by looking at the move times on the Tower of London task, where the point of the task is to go from a start state to a goal state in as few of moves as possible. And the intuition was that if somebody has planned out how they're going to solve this task, they might have a long latency for their first move time as they're trying to think about how to solve it. But then all the subsequent move times should actually be fairly regular because they've thought out in advance how they're going to solve the puzzle. Whereas if somebody is more impulsive or they have poor planning, they might have a very quick first move in order to try to complete the task as quickly as possible. But if they haven't thought it out, they might have made a mistake, take longer for the second move, and there might be more irregularity in their move times. And that is reflected in entropy. So more regular move times would have a low entropy signal. Irregular move times would have a higher entropy signal. And we wanted to look at the same phenomenon in the key presses. So more regular times in between key presses would be a lower entropy signal. More irregular time in between key presses, a higher entropy signal. And the hypothesis were that patients with bipolar disorder who typically have problems with impulsivity and executive dysfunction will have higher levels of entropy in their move times on the Tower of London task. And then that would also be reflected in their keyboard behavior. And we found that patients with bipolar disorder had significantly higher levels of entropy on their Tower of London move times compared to control subjects. And using multi-scale entropy, looking at entropy across different time scales with the keyboard data, they also had higher levels of entropy in terms of their keyboard behavior. And furthermore, those two things were highly correlated in participants with bipolar disorder, such that typing entropy was associated with Tower of London entropy. Furthermore, it was also associated with variability in mood symptoms, variability in impulsive actions and feelings, suggestive that this typing entropy might be reflective of impulsivity that we see reflected in their behavior on the Tower of London task. So we were very happy about this pilot data and thought that it suggested that we can use this passive smartphone data to associate with mood symptoms, associate with cognitive function. And that was the basis of our current R1 study, Unmasked, where we're trying to see if what we measure on the phone tracks with brain network correlates of cognitive dysfunction in a sample of participants across the spectrum of mood disorders. We're also interested to see if we can replicate our associations between keyboard metrics and mood symptoms. And then we have an exploratory aim to see how brain associates with keyboard, associates with clinical symptoms. And here's this basic study design where we're bringing in people for a baseline assessment. They use the app for 2 weeks. Then we do an initial multimodal neuroimaging scan where we're getting diffusion tensor imaging resting state fMRI, and task-based fMRI using a parametric go-no-go task. They also do a clinical and cognitive assessment, and then that process is repeated for another 2 weeks. And this way we can see to what degree what we're measuring with the phone predicts what we can see in the brain and vice versa. All right, and here's an example of some of the hypotheses that we'd like to test. So for example, we've shown that typing speed is associated with processing speed. So we want to see if it's also associated with structural brain network efficiency, which has been shown to be associated with processing speed. Likewise, instability in typing speed, we think is associated with response inhibition. And in a previous paper that we've published, we've shown that reduced nodal efficiency in the ventrolateral prefrontal cortex is associated with response inhibition in a sample of euthymic bipolar patients. And so now I just want to end with a transition into what we're doing, moving into digital intervention with a project abbreviated SPEAK, where the goal is to develop a problem-solving therapy trained chatbot that works using a voice interface. And here is a diagram describing this platform, which we call Lumen. It resides on an iPad, and participants get this iPad as being part of the study. They get to do their PST sessions through the iPad. They can complete surveys, do daily EMA ratings, as well as get educational material and track their progress as they get therapy. We also interface with the participant's smartphone, where we could provide text-based reminders to do surveys, to do their sessions, and then data management is done via REDCap. We're still very much in the early stages of this, but I wanted to play an audio sample from the first session.
Welcome to your first counseling session. Please make sure you have your binder with you so you can follow along. Before we get started with our session, I need you to complete your PHQ-9 and GAD-7 surveys. I texted you the link earlier today. Please complete them now, then restart our session. Thank you for completing your PHQ-9 and GAD-7 surveys. I want to introduce myself. I'm Lumen, your virtual coach. My role is to help you improve your emotional well-being. I will work with you on developing a positive approach to thinking about problems, building skills to effectively solve problems, and plan activities. We will have 8 sessions together and will review your progress along the way.
So I'm working on getting the Samuel L. Jackson version working as well, so we could have some variability in the voices. So we're recruiting patients with mild to moderate depression and or anxiety. They'll get randomized to get Lumen for 8 weeks, so 4 weekly sessions plus 4 bi-weekly sessions, or a waitlist control arm. And we're getting neuroimaging scans done before and after. This is an R61 pilot study where we want to see if our intervention engages both neural targets and behavioral targets. The neural targets are based on previous work done by my co-PI, June Ma, and her colleague Lee Williams at Stanford, where they showed that PST engages specific circuits related to affective regulation and cognitive control. We also have behavioral targets related to problem-solving abilities. And if we show that our intervention, Lumen, successfully engages those targets, then we'll move on to the R33 phase, where we'll add on an additional arm where we'll compare Lumen not only to a control, but to in-person problem-solving therapy. So our hope is with both of these projects, both Unmask and Speak, is that we'll be able to utilize these smart connected devices to passively and obtrusively detect mood changes, cognitive changes, maybe even before they're clinically apparent, and more importantly, intervene, because we know that if we intervene earlier, we have better outcomes for our patients. So I just want to end by acknowledging all the my hardworking colleagues that made this work possible. With the Speak project, my co-PI is June Ma, and we're working with Thomas Kanan Palil, Josh Smythe, and Ben Gerber. And with Unmask, my co-PI is Alex Liao. I also want to acknowledge our funding from NIMH, which has graciously supported both projects. And thank you for your attention.